All right, so we are picking up with 2.1 day 2, and we're going to talk about left and right hand limits. So left and right hand limits are limits that are only being evaluated from one direction. So left or right hand limit is a limit that is only being evaluated from one direction. So the scenarios in which the values of the limit can be different as you approach from the left side versus approaching from the right side. So the left-hand limit is the limit as x approaches a from the left. So you use a negative to represent from the left. So if you think about on the number line, to the left of 0 are the negatives, and to the right of zeros are the positives. So the left-hand limit comes from the negative side, and the right-hand limit comes from the positive side, even though the a value isn't always going to be 0. So a few things need to be true in order for a limit to exist. So a function has a limit as x approaches a. Oh, it's yellow. Can't see that. As x approaches a, if and only if the right-hand limit and the left-hand limit exist and are equal. So that's what this statement is saying down here. The limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the right, so we call this the right-hand limit, equals the left-hand limit, and they both equal L. We can look at this graphically. So if we talk about finding the limit from the left, I just like to draw quadratic functions. They're easy, they're simple, and then we're going to talk about our limit. So if we talk about the limit from the left at some point A, here's my A value. Here's my point A on the graph. The limit of point A is L. If I'm asked to find the left-hand limit, the limit as x approaches a from the left of f of x is equal to L, because we're going to write that quadratic coming in from the left to see what it approaches. We're looking for what it approaches. Only from the left. Conversely, the right-hand limit, and we'll pick it on the negative side just to be. The right-hand limit looks at a graph as you approach from the right side only. So again, the limit as x approaches a from the right-hand side is equal to L. So the right-hand side, you draw your arrow approaching the point using your right hand to the right. The left-hand limit, you start on the left side and go to the right. So you're kind of like drawing from that side, not approaching that direction.
Any 11th grade student with the last name starting with F through Z, please report to the auditorium for your pictures. 11th grade students F through Z, please report to the auditorium to have your picture taken.
There are 3 reasons why a limit fails to exist. We have previously talked about the fact that a limit will fail to exist if the value in the domain jumps. So a lot of times that jump occurs with like an absolute value where it goes from like boom to boom and it jumps around. So there are 3 reasons why a limit fails to exist. The first of which is a jump discontinuity that looks like a piecewise. So number 1, if you were graphing it, might look like this. That would be a reason or a jump discontinuity that would cause a limit to fail to exist. Number 2, f of x increases or decreases without bound. So number 2 is your vertical asymptote. So that would be the case if you looked at a graph and your graph kind of looks like that. It's going down in both directions and the graph does not exist at this point. Like x does, you have a vertical asymptote at x equals a. I don't know why that just zoomed in all funny. Okay. And number 3. F of x oscillates. So an oscillating function is kind of like your Hooke's law, where at the beginning when you drop that spring, it kind of rapidly oscillates like this. And then it teeters off. So like a limit would fail to exist if you have that graph that's like rapidly going up and down. Does that make sense? So those are 3 reasons why a limit would fail to exist. So let's look at a graph and find the limits. So we can look at a graph and know exactly what is happening. So the limit as x approaches -2. So x approaches -2 from the left. So what that means is we're going to look at the graph. F is this top function up here. So this is F. And then this graph down here is G. So F is in red and G is in yellow. So F approaches -2. So here's -2. So we're approaching -2 from the left. So as I get closer and closer and closer and closer to -2 from the left, my limit is 1. As x approaches -2 from the right, so now I ride that roller coaster down from the right side, it's also 1. So if the left-hand limit is 1 and the right-hand limit is 1, then the limit is 1. And this is where it's important to talk about the fact that the limit does not necessarily equal the function value. What is f of negative 2? F of negative 2 is not 1. What is f of negative 2? Where's the closed circle at negative 2? 2. So the limit does not equal the function value. The limit does not have to equal the function value. Okay? The limit as x approaches 1 from the left. Or sorry, g approaches 1. So here's g. I can't trace. Coming in from the left. So from the left, g is going to negative 2. From the right, g is going to negative 1. So the left-hand limit is negative 2. The right-hand limit is negative 1. Therefore, the limit at 1 does not exist. The left-hand limit does not equal the right-hand limit. Therefore, the limit does not exist. This is an example of jump discontinuity because your graph has to jump from negative 2 to negative 1 on your piecewise. This is an example of jump discontinuity. What is g of 1? Where is it closed circled? Perfect. So g of 1 is negative 2. And I know I don't ask you about those values. I'm just trying to get us to think. Okay? The properties of limits say that limits are not limited to just finding their limit value, but that we can add or subtract limits together. We can multiply them by constants. So we can basically apply algebraic properties to limits. So the limit as x approaches negative 2 of 5 g of x plus f of x is similar to saying 5 times the limit as x approaches negative 2 of g of x plus the limit as x approaches negative 2 of f of x. So that limit essentially can be distributed into the problem. So the limit as x approaches negative 2 of g of x. So we go over to negative 2, go to g of x, and the limit from the left and the right is negative 1. So we replace the limit as x approaches negative 2 of g of x with negative 1. We already determined in the previous example C that the limit as x approaches negative 2 of f of x is 1. So the limit of this whole quantity is negative 5 plus 1, or negative 4. The limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x would be 2 times dne. So if the limit of 1 does not exist, then the limit of both do not exist. And I, the limit as x approaches 2, so here's 2, of f of x divided by g of x. So that's the same as saying the limit as x approaches 2 of f of x over the limit as x approaches 2 of g of x. So on f of x, that's like 1.5. And on g of x, that is 1.5 divided by 0 is not dne. Because the limit doesn't not exist. What happens if you get a slope for a vertical tangent where it's a number divided by 0? What do we say the slope is?
And the remaining 11th grade students and 10th grade students, M through R, please report to the auditorium to get your picture.
Exactly.
And the remaining 11th grade and 10th grade students, M through R, who wish to have your picture, report to the auditorium.
So it is not, does not exist. When you get a slope that does that, you tell me it's undefined. So the same is true here. If I have a number divided by 0, it's undefined. So again, I'm sorry I didn't realize in your homework yesterday that 24 through like 28 involved the sine functions. I thought I did a good job of avoiding that. I did not. So the limit as x approaches 0 of sine x over x is a special limit. So we have two of those limits. We have the limit of sine x over x, and then we also have the limit with a cosine. So for now, all you need to know is that the limit as x approaches 0 of sine x over x is equal to 1. The limit as x approaches 0 of sine x over x is equal to 1. A variation of that same limit could occur where you look at something like the limit, and this was what is or was on your homework. The limit as x approaches 0 of sine 2x over sine 5x. So we can kind of manipulate this problem in order to be solved using this rule. So we're going to multiply by x over x to help adjust for this. And then if you want to get it so that we can solve it, we are then going to split our limit using the limit properties we just had. So you have the limit as x approaches 0 of sine 2x now over x times the limit as x approaches 0 of x over sine 5x. What number is inside here that I don't have? 2, right? So for the front limit, you're going to multiply by 2 over 2. We'll write it inside just not to confuse you. And over here, this has a 5 inside. So we're going to multiply this one by 5 over 5. Because the rule is sine x over x equals 1. So if the inside number is something other than 1, then my x value outside also has to include that same number. So now, this one, we can use our limit rule. And what's the value of that going to be? Sine 2x over 2x becomes 1. So you're left with the limit as x approaches 0 of 2 times 1. So it's the limit as x approaches 0 of any constant. It becomes that constant. So this becomes 2. The limit as x approaches 0 of 5x over sine 5x follows the same rule of equaling 1. So it doesn't matter if sine's on top or bottom, that becomes a 1. So you get the limit as x approaches 0 of 1/5 times 1. So we get 2 times a 5th, or 2/5. Yeah, I didn't think I had an example on there. Sorry, I had to squeeze that example in. And speaking of squeeze, we're going to talk about the sandwich or the squeeze theorem. So it goes by both names. And basically it says if you cannot find a limit directly, we may be able to find it indirectly with the sandwich or the squeeze theorem, which basically says that if you have 3 functions, f, g, and h, that you can smush one of the functions in between the other 2. So here we are smushing that pink function, which is g of x, between h and f. So we are smushing that pink function in between the blue and the green.
Any 10th grade student, letters F through Z, who wish to have their picture taken, please report to the auditorium. Again, any 10th grade student, letters F through Z.
So we're going to prove how this works. So we have x squared sine 1 over x. So we know that sine of 1 over x at 0 would give you 1 divided by 0, which makes it undefined at the moment. So what we're going to do is sandwich this between x squared to prove that it's equal to 0. What is the range of sine x? What's the range of our normal sine function? An untransformed sine has a range on the unit circle of what? That's the domain. Think about if you're graphing sine or finding values of sine on the unit circle. What are the extrema of sine? Ooh. One to -1. The unit circle. So if you're thinking about the unit circle, it's okay. These are good things to think about. Think about the unit circle. This point here, this point here, this point here, and that point there. The top points, those are the farthest out on a circle you can be, right? So this point here is 1, 0. This point here is 0, 1. So the highest point is 1, and its lowest point is -1. Well, that's the range of sine. Its highest point to its lowest point on the unit circle. Just like cosine is -1 to 1, because the farthest point left to the farthest point right. So because we know that the range of the unit circle value for sine is 1 to -1, it is fair to say that the absolute value of this function would be less than or equal to the absolute value of x squared. And then if we have an absolute value, we can say that the absolute value of x squared times the absolute value of sine 1 over x, because again, we know that anything squared is going to be positive, so the absolute values are pretty well useless. Is really just less than or equal to the absolute value of x squared, because again, anything squared is positive. And we just determined that the range of 1 over x is -1 to 1. So in terms of an inequality, we could say that -x squared for the -1 has to be greater than or equal to x squared sine 1 over x less than or equal to the positive x squared, because these are technically times your range value of 1. So this is where the sandwich of the two functions comes into play. So this is kind of like the green and the blue function on that graph. If I asked you now to find the limit of all of these, what is the limit as x approaches 0 of -x squared? Plug in 0 and you get, what's the limit as x approaches 0 of x squared? Fantastic. So if the limit as x approaches 0 of -x squared is 0, and the limit as x approaches 0 of x squared is 0, if this has to live between this, and their limits are 0, we can say, ugh, I have to delete this, I need space. So therefore, since their limits are equal to 0, the sandwich theorem says that the limit as x approaches 0 of the two functions that live in the middle of them must also equal 0.
Please excuse this interruption. Any remaining 10th grade student and 9th grade student, letters M through R, who wish to have their picture taken, please report to the auditorium. Again, any remaining 10th grade student and 9th grade, letters M through R.
We could see this graphically if we put it in our graphing calculators. So on your graphing calculator, you could type in Y1, go ahead and put in the upper function, which is x squared. In Y2, you're going to put the function we squeezed, which is x squared sine 1 over x. And then we're going to put in the negative x squared. So you can see here, you have the red, the green, and the blue. And if I zoom in really, really close, we can see that oscillation of the sine function. Getting closer and closer and closer. And can't you see how all of the functions are really going to 0? I'm not very good at Desmos. I don't know how to get, I'd love to show you a table. There we go. So over here in our table, how did we look at a function on our table? You put the point you cared about in the middle, and then you went to the left of that point, negative 0.001, and then you went negative 0.01, or we added 0.01 and added 0.01, and then since this is a weird number, you also added 0.1. Do you see how this number here is getting really, 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 really small? I don't know how to make my table bigger. Can you see how these numbers are getting really, really, really small as we get closer and closer to 0? But yet at 0, it is undefined on that function. Yes, no, maybe so. Okay.